Hey, what's up, guys? So welcome to my topology lecture. So today, previously we already introduced the homeomorphism. Okay, so we should say something about topological invariance. Okay, so you should understand this topological invariant is something that invariant under homeomorphism. Okay, so basically what I'm saying is that you want to have some property that X has a property, say C, and the C is an invariant. So I should say if there's a Y which is homeomorphic to X, then the Y should has the same property C. Okay. So basically something which is you can say something if for example if X is connected, then Y should be the same. Okay. So this is what should be preserved in the homeomorphic. Okay, and there's a lot of them. Some of them, there are so many of them, which is topological quantum field theory, and some of them is very algebraic topology, like the fundamental group. Basically, there's a homotopy group, and you can say ask about this cohomology, the singular cohomology. If your X is a manifold, you can talk about Durand cohomology, and you can also change this Z to be think about something maybe X. Okay, and more generally, if you learn about algebraic geometry, that somebody give you a algebraic variety, then you can take any sheaf and ask about a sheaf cohomology on it. And there's a very kind of version like Z cohomology, and so there are a lot of, right. But in this video, I talk about some two simple property. Okay, so this first one is Hausdorff. Hausdorff is very simple, so let me just quickly say it. Right, so the Hausdorff means that for any, let's say I say that X is Hausdorff, means that for X, Y belongs to X, which they are different. Then there is this the open neighborhood. So this open neighborhood, you cover X and V cover Y. So you get two open neighborhood, which is open set, right? So you can find two open sets. Okay, such that there are distinct, such that they don't have any intersection. So U intersection V is empty. Okay, so this looks trivial in the like usual topology in Rn dimension, because in a Euclidean space, right? You take any 2 points, there should be very small radius that you take any two open ball, they will not intersect, right? But this means that so you should imagine that the Hausdorff should have a lot of open sets such that any 2 points can be distinguished. So I should say any open set has a two open balls such that you can distinguish it. Okay, I think this is also called a T2 space. Okay, and there's an idea called T1 space. So let me just mention it. So T1 space means that there's a for any X and Y which is different, there's a single, so there's an open set for single X. Let's say U of X such that U of X intersection so Y do not belongs to U of X. So T1 space is much weaker than the T2 space. Okay, so which means that, right? So T1, T2 implies T1, right? Because T2 means that the Hausdorff, so any 2 points has to open neighborhood which distinguish them, but the T1 do not. Okay, so this is the so these are also these two are topological invariants which still preserve. Okay, the second another one is the compactness. Okay, so compact means that I think everyone knows about advanced calculus, right? So I mean X is compact. Means that any open cover of X has a finite subcover. Okay, and a very famous theorem that in the calculus that you can check out my calculus video that I will post the link below, which is Henry Borel. So basically, it says that let's say you take Rn, the x in the Euclidean n dimensions, and the x is compact if and only if x is closed and bound. Okay, and in any matrix space, the compact will directly implies closed and bound. Okay, so closed and bound is a simple property of the compact set. Sorry, the compact will simply implies a closed and bound. This can be proved by check out the routine or my videos. So basically, this is trivial. Okay, but the Henry Borel gives you a powerful results that you can use the wire truss somehow, like the Cauchy sequence and the completeness of Cauchy sequence and the wire truss to prove that the closed and bound will implies compact. Okay, and yeah, also there's another theorem that which is very trivial. So if f is continuous and the x is compact, which will map f of x is compact. Okay, so proof is trivial. So you can check out my video. Or okay, so let me just quickly prove it. So let's consider f of x is some finite cover, right? Let's say you get some, you got some cover list, and you can, so x is this. Okay, but f is continuous, so this is just this. So this guy is open. So there is this the finite of length. So I can take this I from one end, which that f inverse vi is open, and the x is, and then I take f, right? So I can get f is a sub is this. Okay, which is finite. So any open covering, it is the finite subcover that I can get from x, and I map it back. Okay, and then there's a theorem says that the closed subset of compact space is also compact. So closed subset C of a compact space K, is also compact. Okay, so this is almost this is trivial in the Rn dimension, right? Because in the Euclidean dimension, that the closed subsets always of the compact set is bounded. So closed and bounded will implies compact, right? So in Rn is trivial. Okay, the reason is the due to the Henry Borel, so HB theory. But generally, general is not trivial. So you can try to prove this. So the general is not trivial. So general is not so trivial. Okay. I think the reason is that actually you can take, since it's closed, right? So it's complement is open, right? So you can put the complement into the any. So let's say K is covered by, let's say, Vi, right? And which I can take the complement of C. So I can take the complement of C, right? So I can try to take the or I should say this. Okay, and so this is K, right? So K is covered by all this Vi, and the C is somehow here, right? So you can try to write, right? So which now there's a finite subcover of K, right? But I mean, it doesn't necessarily means that C has always a finite subcover, because there may be some covering which is do not cover K, but covers C. Okay, so this proof is not okay because I start from K. Okay, so there may be a case that the cover also always only covers C but not cover K. But at any case, you can take the C complement and put in the K. So you will then you can prove these results. It's not it's just simple. Okay, and another one which is connectedness plus connectedness and past connectedness. I think this is also already mentioned in the calculus. So it's also a topological invariant. Okay, so let me just write down definition. So if X is disconnected, disconnected means that if it's union of two disjoint, non-empty open set. Okay. Okay, so yeah, just definition. And there's a theorem. And if it's not, you cannot find the two non-empty open sets such that X is written as union, that X is called connected. So theorem also famous that F is continuous and X is connected. And you can prove that F of X is connected. Okay, and the proof I will not prove here. And also you can define an idea called path connected. So let me just quickly mention. Okay, so path connected. Okay, so path connected means what? So X is said to be path connected if let's say any 2 points in X, right? So let's say take any 2 point X, there is this curve. I should say there's a continuous function from 0, 1 to the space X, such that F0 is X, that the F1 is Y. Okay, so basically this means that for any points in X, you can find a curve such that continuous passing from X to Y, which is path connected. Okay, so theorem that I will not prove here, but I will prove in my analysis video, which that the path connected implies connected, but not vice versa. Okay, so some people like to, so path, basically path connected, yeah. Okay, so path connected implies connected, but not vice versa. So this means that the connected do not imply path connected. Okay, so the idea is that you can, let me just quickly talk about the example that you can consider sine 1 over x. And there's a, you will keep like this. So you will do it like this, and yeah, become something like this. Okay, and yeah, this is one example that this is one example that this function yeah will this function is connected, right? I mean, you can see that you can any two of them, right? You can you cannot separate into two of them, but it's not but the idea is that this is not connected. Okay, it's not connected, right? The reason is that let's say you take 0, 0, right, at some point here, and another point, right? You cannot find a continuous function which f falls into this this point, right? The reason is that at this 0 point, this sine of 1 over x do not actually do not converge, right? So as x goes to 0, your sine of 1 over x does not converge, right? So if you take 0, 0, and let's take another point here, that actually you cannot find you need to go through this curve, right? But this curve will not end up here. Okay, so okay, yeah, so that's it. And I think this is some basic property. See you guys next video.